This is Asif Khan from Georgia Tech. Today I want to connect two topics that are usually discussed separately: the rapid growth of AI infrastructure in space and the device physics of non-volatile memories. My central question is simple. If future spacecraft will feature more AI and must store and process vastly more data on board, can ferroelectric NAND technology provide a more radiation-tolerant path than conventional charge-based flash? I'll begin with the system needs, then focus on our ongoing work on ferroelectric NAND devices, and then I'll finish off with the future directions. The most ambitious version of space AI is Orbital data center. At Davos, Elon Musk argued that space could become a low-cost location for AI within a few years. SpaceX then filed for up to 1 million satellites in the low Earth orbit, while StarCloud, an independent startup, proposed 88,000 satellites. While the timetable might be very ambitious, the direction matters. AI compute is moving closer to where space data is produced, driven by downlink limits, latency, autonomous decision making, continuous solar power, and for defense mission and operational sovereignty. A recent IEEE spectrum analysis provides a useful reality check. A million satellite AI cloud is not simply a terrestrial data center moved upwards. Heat must be rejected by radiation, launch scale debris, radiation, degradation, limited serviceability make the hyperscale vision extremely difficult. But the article also points to practical AI applications that matter now: interpreting Earth observation data before downlink, autonomous orbital operation, and rapid analysis of defense sensor data. These are important space AI use cases, even if orbital hyperscale may take much longer. They also share a requirement that is often overlooked: dependable onboard data storage. The first near-term use case is Earth observation. The problem statement is simple. Satellites generate more imagery, then they can continuously downlink, and for optical missions, cloud can obscure a large fraction of what the camera captures. Sending cloud-covered images to Earth wastes limited radio bandwidth and delay useful data. NISR, a joint NASA-ISRO radar mission, illustrates the overall data scale. It can generate up to 3.25 terabytes of data per day and carries about 1.1 terabytes of onboard storage. For optical imaging, ESS FISAT-1 demonstrated that onboard AI could identify cloud-contaminated images with 96% accuracy. FISAT-2 extends that idea to cloud screening, vessel detection, and image compression. The satellite can therefore prioritize useful information before downlink, while the local storage temporarily holds the images, AI model, and selected results. The second use case is collision avoidance. Earth orbit contains roughly 46,000 tracked objects. More than a million additional debris objects between 1 and 10 centimeters are estimated to be present in the outer space. As this population grows, close approaches become more frequent. Today, collision avoidance coordination can still require emails, phone calls between ground teams, and NASA notes that the process may take several days. NASA's Starlink mission demonstrated a more autonomous approach. During Starlink 1.5, the spacecraft coordinated with SpaceX accepted responsibility for a conjunction and autonomously planned and executed the avoidance maneuver in space. This is an AI autonomy problem in the broad sense, similar to an electric vehicle's autopilot or advanced driver assistance system. Observe the environment, estimate the risk, choose a safe action, and execute within a predefined rules while being in the outer space. The third case is defense. The Space Development Agency's tracking layer is intended to detect and track advanced missile threats from low Earth orbit. Public material describes onboard mission data processing and two-dimensional track formation, followed by low latency relay to tactical users. The AI opportunity is rapid detection and fusion and prioritization without sending every sensor frame through a ground data center. The storage requirement is a reliable rolling sensor buffer, local algorithm, tracks and tracksate, and an authenticated event log that remains intact under radiation. For defense architecture, the onboard processing also reduces the dependence on a continuously available ground link. It can shorten the sensor to decision path and preserve evidence for later verification. This makes latency deterministic access authentication and radiation-induced silent data corruption risk as important as the number of stored bytes. Now let's look at the key memory and storage technologies that are required to make an AI system. AI depends on a hierarchy because no single memory provides maximum speed, maximum capacity, and persistence. At the left is SRAM, static random access memories. The Cerebrus WSC3 integrates about 44 gigabytes of SRAM directly on the compute wafer and delivers roughly 21 petabytes per second of bandwidth. It is extremely fast but comparatively small and volatile. The middle tier is DRAM, dynamic random access memory, particularly high bandwidth memory or HBM. The NVIDIA Rubin example shown here provides 288 gigabytes of HBM and approximately 22 terabytes per second of bandwidth. HBM holds active model tensors, the KV cache, and the working state close to the GPU, but it is also volatile. NAND flash is the capacity tier. A single enterprise solid-state drive now ranges from roughly 30 terabytes to 245 terabytes with a bandwidth around 14 gigabytes per second. NAND is slower, but it is persistent and stores datasets, model weights, checkpoints, and results. The capacity grows by orders of magnitude as we go from the left to the right. Tens of gigabytes of SRAM, hundreds of gigabytes of HBM, and tens to hundreds of terabytes in one NAND solid-state drive. The price is lower bandwidth and greater distance from the processor. AI performance depends on moving information efficiently across the tiers. The drawing shows a simplified AI pod. In the center are 6 GPU compute racks. If each is comparable to an NVIDIA GB200 NVL72 rack, each rack contains 72 Blackwell GPUs and about 13.5 terabytes of HBM3E. Across 6 racks, that is 432 GPUs and roughly 80 terabytes of HBM. Beside the compute section are 2 blue racks dedicated to shared NAND flash storage. Those storage racks hold the much larger persistent tier, training datasets, model weights, checkpoint embeddings, and generated results. Their exact capacity depends on the storage platform and drive configuration, so the image should read as an architectural illustrations. As a real reference, NVIDIA's EOS supercomputer uses 12 petabytes of NAND flash storage in fewer than 3 racks. The backend RDMA network connects the compute and the storage racks, so hundreds of GPUs can read data and write checkpoints in parallel. GPU racks may still contain small local SSDs for boot caching or temporary data, but the 2 blue racks represent the shared bulk NAND tier. Separating them makes it possible to expand persistent capacity independently on the GPU count while keeping the data available to the entire pod. At campus scale, the storage requirement reaches exabytes. Consider Meta's planned Hyperion campus, which is designed to scale toward 5 gigawatts. Using the planning assumption shown here, Hyperion would require approximately 15 exabytes of installed NAND storage. This is an estimate, but that makes the scale intuitive. 1 petabyte is 1000 terabytes. 1 exabyte is 1000 petabytes. Therefore, 1 exabyte equals 1 million terabytes, and 15 exabytes is 15,000 petabytes or 15 million terabytes. That is equivalent to more than 60,000 of today's 245 terabyte enterprise SSD. HBM and DRAM are not included in this estimate. The key point here is that large AI infrastructure requires an enormous amount of persistent storage tier, and an orbital version would need to provide those bytes with a much tighter limit on mass, power, cooling, and radiation protection overhead. The workhorse technology for data storage is the 3D NAND technology. In the 3D NAND structure, a vertical polysilicon channel passes through a stack of wordline metals. Around the channel are the tunnel oxide, the charge trap layer, and a blocking oxide. Each wordline forms one memory cell around the vertical channel, and many cells are connected as a NAND string. The data is stored in the charge trap layer as trapped charges, primarily electrons in the program state, and with the electron removed or positive whole charge contributing to the erased state. Changing the amount and the sign of the trapped charge changes the transistor's threshold voltage. The controller reads the threshold voltage and maps it to a digital state. Instead of scaling only lateral across the wafer, industry adds vertical cell layers, placing many memory cells within the footprint of one vertical channel. In the cross section, this resembles a cylindrical gate-all-around transistor repeated vertically. The memory layers wrap around the channel, and each horizontal word line selects one level. A single vertical hole can therefore contain a long string of cells. Manufacturers repeat the structure across the wafer and across multiple bonded decks, turning vertical height into bit density. 3D NAND is currently the only mainstream semiconductor technology that is truly three-dimensional in its structure. This is not simply a stack of separately packaged chips that are stacked on top of each other. Rather, the memory cell string itself extends vertically through the structure. The commercial transition from 2D to 3D architecture occurred around 2014 when Samsung introduced its first generation 24-layer multi-level cell vertical NAND and then expanded production. In roughly 1 decade, the industry moved from 24 layers to production technologies approaching 300 layers, and the current roadmap are already targeting 1000-layer class structures through multi-deck processing and wafer bonding. The manufacturers also increase the number of bits stored in each cell. The current commercially shipping capacity benchmark is Micron's 6600 Ion Enterprise SSD, 245.67 terabytes of usable capacity, using Micron's Generation 9 three-dimensional quad-level cell NAND. Micron describes it as the highest capacity commercially available solid-state drive. Let's now move on to the question why space NAND is hard. NAND stores information as electronic charge in the charge trap layer in the form of trapped electrons or holes. Those charges are very sensitive to radiation. Ionizing radiation creates electron-hole pairs, changes oxide and interface trapping, and can remove or redistribute the charge that represents the data. The resulting electrostatic change shifts the cell threshold voltage. In triple-level cell NAND, 8 narrow threshold voltage distributions encode 3 bits per cell. A radiation-induced shift can move a cell across a read boundary, so the controller interprets the cell as a different digital state. Radiation can also affect the peripheral circuits that generate high voltages, control, read, program, and erase operation. In NASA's heavy ion testing of modern 96 and 176 layer commercial NAND, programmed states were observed to shift toward the erased state. Changing the read reference voltage reduced some of the apparent error, confirming the radiation had displaced the cell's threshold voltage. The vulnerability of standard NAND technology is therefore related closely to the fundamental physics of how data is stored in these devices. Today, engineers compensate at both the cell and system levels. TLC can be operated as a pseudo SLC, using only 2 widely separated threshold states instead of 8. Because TLC normally stores 3 bits per cell and pseudo SLC stores only 1, the raw capacity penalty is approximately threefold. Systems then add error correcting codes, scrubbing, block retirement, redundancy, shielding, monitoring, and robust controllers. These methods are effective, but they shift reliability into overhead around the array. The dense NAND still stores charge, so protection reduces risk rather than removing the underlying radiation interaction. Pseudo single level cell also improved endurance and write performance because the controller uses a wider portion of the threshold voltage space. But the trade-off is real. One physical TLC cell now carries 1 logical bit instead of 3. Redundant copies, spare blocks, strong ECC consume additional effective capacity. This explains why a reliable space storage system has a much smaller usable storage capacity than its actual design capacity. True space qualified SLC NAND is commercially available. One example is the Radiation-Tolerant NAND family from 3D Plus, a French high reliability electronics company. These packages provide 8 to 128 gigabits, which is 1 to 6 gigabytes, and space qualified S-level screening is available. The family specifies more than 60 kilorad of silicon total ionization dose latch-up threshold above 62.5 millielectron volt centimeter squared per milligram and 100,000 program erase cycle and 10-year retention. Here 3D Plus refers to stacked packaging. The vendor does not publicly identify the NAND die supplier or whether the internal cell is planar or 3D NAND. Assurance is high, but the capacity remains in gigabytes per package. The product is radiation tolerant, not radiation immune. Its specified single event upset cross section is non-zero, so mission designers still need error correction code, scrubbing, and a qualified controller. Package level screening also does not identify any internal die characteristics. The key distinction is procurement assurance. These parts are supplied with space-oriented screening, radiation specifications that ordinary commercial solid-state drives do not provide. At the other extreme is HP Spaceborne Computer 2 on the International Space Station. Its refreshed 2024 configuration carries around 134 terabytes of nominal Kioxia solid-state drive capacity, 4 30 terabyte PM6 SAS drives, 8 1 terabyte XG6 NVMe drives, and 4 960 gigabyte RM6 drives. About 90% came from the PM6, which uses 96 layer 3D triple level cell NAND. Kioxia states that the SSDs were commercial and not customized for space. They were not operated as pseudo SLC. Daily health logs made this practical inside the protected serviceable ISS environment. These demonstrate capacity, not intrinsically radiation qualified NAND. This environment matters. The drives operate inside pressurized ISS behind the station structure with stable power, active thermal management, routine telemetry, and the possibility of human servicing or replacement. A free-flying deep space data center would lose many of these protections. The demonstration answers whether commercial flash can deliver useful capacity in this particular orbital platform, and it does not establish a universal radiation tolerance that will be required for orbital AI data infrastructure. This slide compares the orbital data infrastructure with those on Earth. As we showed in the previous slide, the flown HPE International Space Station system is above 130 terabytes. Axiom and SpaceBuild have announced an International Space Station orbital data center node above 1 petabyte for 2027. On the other hand, on Earth, one shipping Micron SSD holds 245 terabytes, and 20 such drives provide more than 4.9 petabytes on one rack unit. So, on one hand, Orbit is approaching petabytes of storage. On the other hand, on Earth, the terrestrial infrastructure spans to exabytes. So there is a big gap to fill up there. So let's ask the question why ferroelectrics might provide a better NAND storage solution for space applications. A ferroelectric material is an insulating material which is also crystalline. And most importantly, the crystal structure is non-centrosymmetric. The central ion is off-centered from the center of symmetry. As a result, at the unit cell level, there is an electric dipole in this material, and the direction of the electric dipole can be switched by applying an electric field larger than the coercive field. As a result, at a zero voltage or a zero electric field condition, it can be in one of the two bistable states. As a result, it can work as a non-volatile memory. Now, this bound polarization state can be more tolerant to radiation effects than charge trap that are used for data storage in conventional NAND technologies. Here is a device level comparison between charge trap based flash and ferroelectric flash. In a charge trap flash, programming and erasing add or remove electronic charge from the trapping layer, shifting the threshold voltage. In a ferroelectric field effect transistor, programming and erasing switch the polarization direction in the gate stack, which changes the channel electrostatics and produces a similar threshold voltage shift. The readout is familiar in both cases, two transfer curves separated by a memory window. That compatibility is important. A ferroelectric gate stack could preserve the vertical NAND streak concept while changing the physical variable that stores the bit from trapped charge to polarization. In both devices, the system ultimately reads a threshold voltage, so the external NAND concept can remain the same. The crucial difference lies within the gate stack. Charge trap NAND relies on tunneling electrons into the insulating layer. Ferroelectric NAND applies an electric field to reverse the polarization. If that stack can be wrapped around a vertical channel with acceptable voltage endurance and variation, the NAND architecture can retain the NAND density while significantly improving its radiation response. The motivation for ferroelectric based NAND flash technology is broader than its potentially improved radiation tolerance. Terrestrial charge trap NAND faces scaling pressure, lateral charge migration, high voltage programming, and oxide wire coupling and pass disturb channel variability that compresses the read margin. Ferroelectric NAND technology may address some of these commercial challenges while also offering radiation resilience. So our group started working on the ferroelectric NAND flash concept in 2022. We see the targets from a geometry and operation of vertical NAND. The memory hole for a 3D NAND architecture is roughly 80 to 100 nanometers. So the complete gate stack needed to stay below around 19 to 20 nanometers. We wanted the program and erase within a plus minus of 15 volts and the memory window above 6.5 volts to make it compatible with 3 bits per cell or 4 bits per cell operation plausible. These are the design targets. They force us to pursue a thin stack with a large and controllable window. We first built ferroelectric field effect transistor with silicon channel as a control test platform. The active gate stack consists of two ferroelectric hafnium zirconium oxide layers sandwiching an aluminum oxide insert. The process includes source drain implantation, ferroelectric thin film deposition using the atomic layer deposition technique, rapid thermal annealing, and back-end contacts. The cross-sectional microscopy confirms that the laminated stack and its interfaces are physically realized at the intended nanometer dimension. This test structure lets us optimize the gate stack. The first memory window experiment compares a uniform 19 nanometer HZO film with a laminated 919 stack, 9 nanometers of ferroelectric hafnium zirconium oxide, 1 nanometer of aluminum oxide, and 9 nanometer of ferroelectric hafnium zirconium oxide. The total thickness remains 19 nanometers, so the comparison isolates the dielectric insertion rather than simply adding a material. The microscopy on the right verifies the thin aluminum oxide layer between the two ferroelectric regions and the interfacial oxide at the silicon. The 1 nanometer dielectric insert increases the memory window significantly. The uniform 19 nanometer hafnium zirconium oxide device reaches a memory window of about 3 volts. The 919 laminated stack reaches about 5.3 volts at a similar total thickness while remaining within the 15 volt right voltage target. The insert redistributes the electric field, changes the switching behavior, creates an internal electric field, allowing a larger threshold separation or a larger memory window. This moves us from a memory window consistent with roughly 2 bit per cell operation toward a 6.5 volt target that we associated with 3 bit per cell NAND operation. The aluminum oxide layer is not a ferroelectric. It changes how the applied voltage divides across the stack and how the two HZO regions switch. The result is greater threshold leverage without exceeding the geometric budget of 19 nanometers. We then increase the aluminum oxide insert thickness from 1 to 3 nanometers while keeping each HZO layer at 8 nanometers. The 838 structure produces the largest result, a 7.3 volt maximum memory window at a 14 volt write pulse. That exceeds the 6.5 volt target while keeping the full ferroelectric plus the dielectric thickness at 19 nanometers. We then studied how the choice of the dielectric material insert, its position, and the thickness affects the memory window. The largest memory window we could achieve was around 10 volts, which can enable quad-level cell operation. Nonetheless, the results in this slide show that there is a lot of room for engineering the gate stack for enabling ferroelectric NAND technology. This field has now expanded well beyond one stack. Academic groups are exploring tunneling and blocking dielectrics, different interfacial layers, hybrid ferroelectric structure, alternative channels, and vertical integrations. There has also been a lot of work on co-optimization of the memory window, write voltage, and the reliability aspects such as write endurance, retention, and disturb, all for NAND applications using ferroelectrics. Industry is also exploring the same direction. SK Hynix, Samsung, and Micron have all reported ferroelectric three-dimensional NAND concepts for demonstration. Their structures and maturity differ, but the common signal is important. Ferroelectrics are being evaluated within the realistic vertical strings and manufacturing flows. It means the density and integration case is credible enough that major NAND manufacturers are investing in it, which strengthens the opportunity for a space-oriented radiation-resilient variant of 3D ferroelectric NAND technology. We summarize this rapidly developing landscape of ferroelectric NAND in our recent MRS Bulletin article. This article evaluates how ferroelectrics may enable the next phase of extreme scaling of 3D NAND technology. All right, Now we move on to the radiation study of our ferroelectric NAND devices. For the radiation study, we used laminated 838 ferroelectric field effect transistors and cobalt-60 gamma radiation. Devices were written into programmed or erased state, characterized, and then exposed at approximately 112 kilorad in air per hour to total doses of 1 and 10 megarads. We examine the stored state stability, memory window, incremental programming and erasing, retention and disturb. These are discrete device total ionizing dose experiments. They test whether the polarization based cell itself retains useful behavior under extreme accumulated dose. The very high doses are intentional. They expose weak mechanisms and create margin relative to many mission requirements. The timing of the experiment matters. We measure threshold voltage shortly after writing, transport the sample, irradiate it over several days, and measure again roughly 30 days after the original write. A matched device remains unirradiated for the same interval. That control separates the radiation damage from ordinary temporal effects such as depolarization and imprint. The meaningful quantity is not simply the before and after shift, it is additional shift in the irradiated sample relative to the time-matched control. The control and the irradiated device follow the same handling and weighting schedule. This makes the elapsed time drift a measured reference rather than an unqualified experimental artifact. The unirradiated control establishes that baseline. After 30 days, the erased state is nearly unchanged while more strongly programmed states move towards lower threshold voltages. We associated that program state relaxation mainly with the depolarizing field and the normal retention behavior. This is why a control is essential. Without it, one could incorrectly attribute every threshold voltage change after sample transport and delay to radiation. The asymmetry between the erased and the program relaxation also warns us against describing the stability with only one state. The useful memory window depends on the movement of the threshold voltage for both the programmed and erased states. The 1 megarad in air result closely tracks the control. The erased state remains stable. The programmed state movement after 30 days is comparable to the unirradiated relaxation. We therefore observe no clear additional TID loss in the stored states in 1 megarad. At 10 megarad, a distinct dose effect emerges. The erased state shifts more than the control and 1 megarad samples, while the program states remain dominated by the same depolarization related relaxation. The behavior is asymmetric, which points to the radiation created traps and interface electrostatics, then a simple destruction of the ferroelectric polarization. The conclusion is that the useful polarization based state remain robust through 1 megarad and degrade only at a much more extreme accumulated dose. Even at 10 megarad, the device remain electrically functional. The observed shift identified interfaces and trap charge as improvement targets rather than showing catastrophic loss of ferroelectric switching. Next, we asked whether the device can still be programmed and erased after irradiation. The control 1 megarad and 10 megarad devices were retained using the same plus minus 15 volts, 10 microsecond pulses, and the threshold voltage were measured 1 second later. Both threshold voltage distributions shift somewhat with the dose, but their separation remains almost unchanged. The extracted memory window is 5.57 volts before irradiation, 5.61 volts after 1 megarad, and 5.39 volts after 10 megarad. Therefore, even after 10 megarad, the devices can still generate essentially the same full memory window. Importantly, this experiment measured post-irradiation programmability. It is different from asking whether the data retained before the irradiation remains unchanged. A large final memory window does not mean that the programming dynamics are unchanged. We use incremental step pulse programming and erase, or ISPP and ISPE. Instead of applying one large pulse, the pulse amplitude is increased in 1 volt steps and the threshold voltage is measured after each step. The slope tells us how efficiently each voltage increment changes the threshold voltage. Both the program and erase slopes decrease after irradiation, with the erase slope showing a larger degradation. This means that the irradiated device requires larger voltage increments, more pulses, or modified verify algorithms to reach the desired threshold voltage state. Thus, the full memory window remains available, but the programming and erasing become less efficient as the dose increases. This slide examines retention after the irradiated devices are written. The programmed and erased threshold voltages are monitored at room temperature for approximately 10,000 seconds. All three devices retain a clear separation between the two states, but the states gradually move toward one another. The memory window loss after 10,000 seconds increases from approximately 3% without irradiation to about 9% after 1 megarad and about 19% after 10 megarad. We attribute this increased relaxation primarily to detrapping of charge associated with the ferroelectric aluminum oxide interfaces. These interface charges help enlarge the memory window, but the radiation creates additional defects and modifies their trapping dynamics, so their relaxation produces greater retention loss. Therefore, retention remains functional, but it becomes progressively weaker with TID. Disturb is especially important in NAND technology. To read one selected cell, the other cells receive a pass voltage, typically several volts, to turn them on. Repeating those pass pulses can slowly alter the unselected cells. The schematic separates read disturb in a selected device from pass disturb in its neighbor. We therefore apply repeated 5.5 volt pass pulses after programming or erasing and track the threshold voltage movement versus cycle count. Pass disturb occurs because reading one NAND cell requires a pass voltage on the unselected cell of the same string. Here, each device is first written into either the programmed or erased state. A pass voltage of approximately 6 volt is then applied repeatedly for 50 microseconds for up to 1 million cycle. The erase state remains relatively stable, but the program state threshold voltage shifts upward because the repeated pass pulses trap electrons near the channel side interlayer. The control and 1 megarad device show comparable disturb behavior. A noticeably larger shift appears only after 10 megarad, increasing from approximately 0.7 volt to approximately 1.1 volts after 1 million cycle. Thus, pass disturb remains robust through 1 megarad but begins to degrade at extreme 10 megarad dose. This slide is the main summary of our nanolaters paper led by Lance Fernandez. When the threshold voltage degradation is normalized by dose, the laminated ferroelectric NAND cell is roughly 30 times less sensitive to total ionizing dose than charge trap NAND benchmark. The memory window remains essentially stable through 1 megarad, while conventional charge trap NAND flash storage is directly disrupted by radiation generated trap at that level. The paper describes the device design, irradiation protocol, stored charge, retention, programming, and disturb result behind that comparison. The 30 times comparison is based on normalized threshold degradation per unit dose, so it compares the sensitivity rather than two tests performed at two different doses. The contrast between the charge trap benchmark and ferroelectric NAND devices, as we observed in this work, is large enough to establish a compelling mechanism level advantage of ferroelectric NAND for radiation tolerant storage applications. So finally, what are the next steps towards a truly flight qualified ferroelectric NAND technology? We must go beyond gamma total ionizing dose to heavy ion single event upset effects, possible gate rupture at plus minus 15 volts, ferroelectric specific polarization upset, proton and neutron displacement damage. Second, we must combine radiation with cycling, imprint, temperature bias, and long-term retention. Third, we must move from planar devices to vertical strings, arrays, and measure raw bit error tails and harden charge pump decoder, sense amplifier, and controller. Finally, predictive models need independent trap metrology and side-by-side ferroelectric NAND and charge trap benchmarks in the same radiation chamber. 1 megarad cell resilience is the starting point. The first workstream is single event testing. Heavy ions can deposit charge locally, trigger latch-up in peripheral CMOS, or create destructive rupture of the device under high electric field. We also need to determine whether a particle can nucleate a local polarization reversal, a failure mode unique to ferroelectrics. The second workstream is combined stress. Real cell arrive in orbit after fabrication, cycling, imprinting, aging. Irradiation must be performed under bias across mission temperatures, followed by accelerated retention. The third workstream is architecture. We need vertical macaroni channels, complete NAND strings, distribution tails, error correcting code analysis, and radiation hard high voltage generation. The fourth is mechanism validation. Charge pumping DLTS, EPR, XPS, and control CTF comparison should replace adjustable fitting parameters with measured trap population and physically predictive models. I'll close with 4 points. First, AI is moving into space, and onboard sensing, inference, and autonomy require persistent, trustworthy storage in space. Second, conventional NAND is not intrinsically radiation tolerant. Qualified true single-level cell products can exceed 60 kilorads of TID, but their capacity is measured in gigabytes per package, not in terabytes. Third, ferroelectric NAND replaces trapped electronic charge with switchable polarization, and our cell-level memory window remains nearly stable to approximately 1 megarad. Fourth, the work is still in progress. Heavy ions, combined stress, retention, vertical arrays, error statistics, and radiation hard peripheral circuits must be addressed before flight qualification. This brings us back to the opening question. Orbital AI is not only a processor problem, its usefulness depends on whether data and state survive between sensing, computation, and downlink. Today, we can choose a small qualified single-level cell or a large monitored commercial triple-level cell NAND technology. Our work on ferroelectric NAND suggests a third path. Pursue data center-like density while moving a substantial part of radiation resilient into the storage mechanism itself by adopting and developing the ferroelectric NAND technology. Finally, this was a team effort. The work was primarily led by Lance Fernandez. I thank Lance, Prasanna, Salma, Taeyang, Zekai, Hang, and all of the students and colleagues shown here for different aspects of the work. I especially thank our collaborators, Professor Douglas Wolf at Penn State and Professor Bishwajit Ray at the University of Colorado Boulder. This work was supported in part by Supreme, one of the 7 centers in JUMP 2.0, a semiconductor research corporation program sponsored by DARPA. The breadth of the names on this slide reflect how multidisciplinary the work is, from material and fabrication to electrical testing, radiation testing, microscopy, and system interpretation. I'd be happy to discuss the results and qualification roadmap in the questions.